Thank you for coming to the talk. Please stay muted and keep your video off as we'll be recording this talk. If you are having technical problems, PM me or Alison. But if you have math questions related to the talk, please PM Chris at chris-nymc. Let's see. We're happy to have Chris here today. He's from Seattle and he's a friend of New York Math Circle. He's been actively involved in mathematics competitions and problem solving for over 25 years, both as a competitor and as a problem writer and editor. He currently writes problems for and proofreads many high school and middle school math competitions. He's an instructor for the MSHS Summer Program and currently serves on the AMC, AMY, and ARML boards. So without further ado, welcome, Chris.
Yes, thank you very much, Kovin, Dr. Pillay. And thank you very much to Dr. Pillay and Ms. Mack for organizing this guest lecture. I am actually not in New York right now. I went to school in New York. I'm actually broadcasting to you, and I'll switch to my live feed so you can see me, see who I am for just a second. Get that working. Okay. Give me a sec with the technical difficulties. Okay, so welcome, and I wore the closest shirt to I Love New York today. It's a shirt created in my home state of Washington. I'm broadcasting to you from Seattle, Washington, so I, the imaginary root, and then this is a cardioid, a polar curve, and then math, so I love math. I do actually have another New York shirt that maybe I'll change it when I'm off camera during the show. So I'm very glad to be returning to the New York Math Circle. You probably see on your screen an opening problem that some of you have worked on and have messaged me your answers. Just a few ground rules to get out of the way. If you should disable your video because we are recording this. And we don't want people's personal information to show up. What else? Yeah, I'm gonna pin this video. And okay. When you think you have an answer to a question, private message me. I'll be at the top, and I am Chris-NYMC. You can just call me Chris. And definitely do not message everyone. I think we've disabled that ability because then it sort of just goes out of control. So this is my 5th time doing a guest lecture in the last 5 years for the New York Math Circle. It's great to be with you virtually. I wish I could be here in person. Unfortunately, these are the times we live in. But we're going to have a lot of fun today, and we're going to do something a little different. This is going to be more like a workshop style lecture. So if you think about classes that you have at the New York Math Circle or at school, very often the theme of a class is that you learn about a technique or a certain insight or an idea, and you apply that to solving a variety of problems. Or maybe you learn problems about a certain topic. Like today we're going to learn about circles, or today we're going to learn about modular arithmetic or inclusion-exclusion principle. And indeed, the theme of my previous talks have been things like, I did a geometry one the first year, distance from a point to a line. I did something on maximum and minimum without calculus, which was kind of cool. I did something on graph theory. I did something on algorithms. What this opening problem illustrates is that not all problems have sort of a known answer. Now, of course, these problems that I'm showing you do, that's sort of the subtext, otherwise that would be sort of a cruel thing to do to you. But the point is that these are open questions. Find an example. If no such example exists, explain why not. And that's sort of shorthand for prove it. And part B follows the same kind of reasoning, except I make a slight variation in a condition. So to give you a sampling of what mathematicians do, and I'm actually not a professional mathematician. I went to Cornell and got a bachelor's degree in computer science. My day job is working at Microsoft, but I love doing these lectures and guest lectures on the side, as well as teaching on the side. So, but I know enough about mathematicians professionally to know that very often they're researching questions for which they really don't know, is it true or not? And so either if it's true, they should prove it. If it's not true, they should be able to disprove it using a counterexample. So we're going to get into that. So just for the purposes of warming up, because I know there's a range of different ages in this audience. If I were to make the statement that all animals have 4 legs, first of all, true or false? So private message, false. Okay, so if it's false, then, okay, give me a counterexample. Convince me it's false. Great, okay. So chicken, fish, you know, but you could see some evidence for why it would be maybe true, because look at animals that have 4 legs. Frogs, horses, giraffes, elephants, cows. So it could be true, but the point is when we say all, we mean for every animal, that animal must have 4 legs. Okay, so even people, you know, people, if you consider those animals, we have 2 legs, okay? So what if I said, okay, everything that has 4 legs is an animal? Do we think that's true? No, yes, no. I said everything, so I'm not even saying animal. Okay, so people are saying we think it's false, and maybe the best counterexample is could be a chair, could be a table, something like that. Okay, so I think you get the idea of finding examples or counterexamples for these open questions. So for this one, part A, I'll just, I'm gonna write on the paper, and you'll see my writing on the screen as I'm writing it. There are lots of examples that actually do work, so this is true. If we started at like maybe the easiest multiple, 4-digit multiple of 7, that would be, let's say, 1400. Well, that won't work because 0 is actually a multiple of 7. 0 is 7 times 0. So we could add 7, but now we have 2 bad numbers still. We have a 0 and a 7. We could add 7 again, and now we don't have any multiples of 7, but everything, we have 2 repeats. We have the 1 is repeated, the 4 is repeated. If we add 7 yet again, okay, now we're getting better, but we still have the 1 repeated. And then finally, if we add 7 one more time, we have 1428, which is one example among many that will work. You could think about how do we count the number of such numbers. I don't know that that's an easy way to do it without some brute forcing. And what else do I want to say on this one? So, well, as one student pointed out, they sought the smallest counterexample. That's often something that is interesting to think about. Obviously, it can't be in the 1000 range because of the 0. It can't be in the 1100 range because you have 2 1s. So we start to look in the 1200s for multiples of 7, maybe working our way up until we get one with different digits, none of which is a multiple of 7. So I'll leave that as a little exercise. What if I suggested that this is a counterexample? Do we agree that this is a counterexample? I mean, digits are different. No multiples of 7. Why doesn't this work as a counterexample? It's not a multiple of 7. If you look backwards from 1400, our multiple of 7 that immediately precedes 1400 would be 1393. Which that of its own won't work because we have 3 repeated, okay? So we have to make sure that when we present a counterexample that it satisfies all of the conditions, namely Roman numerals 1, 2, and 3, okay? So it fails basically the condition 1. Okay, so the way this is generally going to go is I'm going to flash a problem on the screen, And you're going to spend a minute, 2 minutes, maybe sometimes 5 minutes. We'll go various difficulty levels, okay? And some of them are going to go very quickly. Some of them are not going to go so quickly. And what I'd like you to do is private message me when you think you have a guess as to is it true or false, or whatever the immediate answer is, and then message me when you think you have either a example, counterexample, or a sketch of a proof. You don't have to write out because it's kind of hard to write a lot in Zoom chat. What else do I want to say? Just so you know, we're recording this, so you'll be able to see the recording. Everything that I'm showing you that is printed, that is on this document camera, there will be a handout that will be getting sent to the organizers, and they will share this with the math circle at large so that it will be available in like one nice sheet. And we're not even going to get through everything because, well, it's, I think even 1 hour is going to go by pretty quickly, but if there's interest, which I hope there is, we'll go anywhere from 90 minutes to up to 2 hours. It sounds like Dr. Pillay has a hard stop at 4 o'clock. So that'll be sort of our game plan. I haven't yet talked about B. One thing I want to say before we talk about B and then move on to our first problem to try out, I want to say two things. First of all, because there's over 100 attendees, and I'm so gracious and grateful that you showed up to listen to me. I hope this is fun and engaging. On the other hand, there's only one of me, and it's going to be very hard for me to address and respond to every comment. It's even hard when I'm teaching right now, and I'm teaching a dozen students to address every comment, but I managed to do that. But this is going to fly by pretty quickly. The other thing I would like to say is these examples, this one I would say is number theory and just maybe a little bit of logic. We're going to run the gamut of all four kind of, I like to affectionately call them math food groups, which is to say that there will be examples in this if you don't like number theory. We have a lot of number theory, but we also have a lot of geometry sorts of problems that are open questions. Is it true? Is it false? Show me. Some algebra, and we even have some counting questions that are of this style. Okay, so sound good? All right, so now just to talk about B very quickly. B ends up being false, as some of you have pointed out. If you write the general form, and I'm kind of sketching proof outlines, these are not like necessarily rigorous proofs that you would necessarily write on a essay contest or an Olympiad. But if I sketched out the general form of a 4-digit rep unit, that means just the digit is repeated. So if I say that a general number of this form is D, where of course D can't be 0 because it's a 4-digit number, so the leading digit isn't 0, but also because of condition 3, we have that D is not equal to 7. Oh, thank you. I appreciate if people are saying, tell me, can't see page. So yes, thank you. If that should happen, please do message me. Appreciate that. Okay, so general 4-digit number, 4 Ds in a row. The underline just means it's digit concatenation, not multiplication. And we know that the leading digit can't be 0 because it wouldn't be a 4-digit number. And 7 is also a forbidden digit because of condition 3. Okay, well, if we sort of thought about the decimal expansion of this and factored it, this ends up being D times 1011, 1111. And that factors as D times 11 times 101. Well, we want to satisfy the first condition. We've clearly, by our construction, satisfied the second condition. Well, we know that D can't be a multiple of 7 because of condition 3, so that rules out 0 and 7. And then our other factors are prime, 11 and 101, and there's no multiples of 7 in there, so we're done. So that's how this is going to go. So I will, in general, have the thing at this top to private message me for your work, your progress, and let's get started. As soon as I can find my, okay. All right, and here we go. Let me know if you can't see this. So maybe the first question is, do we think it's true? And by true, I mean true for all possible selections of A, B, C, and D. So sometimes there's a variety of problem that is asked in textbooks or even in competitions, which is it sometimes, always, or never true? So I'm just framing it as a general result. If these are arbitrary real numbers, I get to pick what they are. You have no idea what I'm thinking. Is it universally true, or is there at least one case where it's false? And if we think it's false, which it seems like that's what's coming in, that's the dominant answer, then we should be able to produce an example that convinces ourselves that it's false. Okay, so I'm just going to pick one here. So A equals 10, B equals 9, C equals 8, D equals 0. Well, we certainly have A greater than B, so this hypothesis is satisfied. We certainly have C greater than D, so that hypothesis is satisfied. And now let's take pairwise differences. A minus C, that difference is 2. B minus D, that difference is 9, okay? And in a way, you can kind of see why this shouldn't, well, it might be tempting to think, well, it's an inequality. You should be able to do the same thing to both sides, but I focus on the prefix in, not an equality. So the rules for equations do not always universally apply to inequalities. And in particular, if C is greater than D and I multiply by -1, I get negative C, and then I have to, as you probably know, reverse the sign of the inequality to make that true. So can you combine these two to form a conclusive result? Well, the problem is that the inequalities are pointing in the opposite direction. So therefore, we cannot make such a blanket statement like this. One thing I'll just mention is, or just throw out is, then you might say, okay, well then is it always false? Is it always the case that this should be a less than or equal to? And I think that people have already caught on to the fact that no, it can sometimes be true. It's just not always true. Okay, next problem. It'll be another algebra one that's up. Just have to find my stuff. Forgive me, but I have a lot of paper hanging around and things get lost very quickly. My goodness, where did this go? Oh, sorry, I put it on my laptop. Okay. How about, let's do a number theory one again. Actually, yeah, well, let's do number theory. So about half of these I just wrote on my own, including this one. And it was inspired by this idea that you probably know that to test for divisibility by 3, you add up the digits. And if that's a multiple of 3, then so is the original number. And it's an if and only if. And to test for divisibility by 9, it's the same thing. Like you add up the digits, and if that's a multiple of 9, then so is the original number. So I'm thinking about powers of 3, and I'm wondering, well, I'm wondering if the next power of 3, 27, if we could do this. So part A asks, if I have a multiple of 27, am I guaranteed that its digit sum is 27? So let's see what we got. So this is no. simplest example is 27 itself, which gives S of 27, apologies, I'm left-handed, is 9. And 9 is not a multiple of 27. It's a factor of 27, but not a multiple. Okay. Part B is asking the converse implication. Well, suppose I have a number and I know that the sum of its digits is 27. Like, what would be the smallest number whose digit sum is 27? That should be a pretty easy one. Yeah, 999. And we can factor that as 9 times 111. And 111, even if we don't know how to factor it, we know that it's a multiple of 3, ends up being 3 times 37. So 999 works, but I guess I'm asking in general, for every number whose digit sum ends up being a multiple of 27, does that number also have to be a multiple of 27? So what do we think the answer will be? I'm getting yeses, no, true. I'll cautiously say yes. So this one takes a little longer to think about. So this, and I should have said this right off the bat, which is, it's either going to be true or false. And the answer is going to be either known or it's going to be an open, unsolved problem. I will tell you that this is a solvable problem. So the answer is known to me, and it is not hard to convince ourselves of the correctness of the answer. But assuming that you get a question that is open, you have to decide, is it true or false? If it's true, I find an example or a counterexample. If it's false, I find a counterexample or a proof, you know, like you do whatever is appropriate for the context. For the known problems, it can only be, what am I trying to say? Well, it's either going to be true or false, and one of those will be impossible to establish. So if you have a very hard time finding a counterexample, maybe it's true. And if you have a very hard time finding a proof, maybe there's a counterexample out there. Okay, so I had my most recent message that came in said that it is false, and so does it follow? This is also no. So this is in general not a true divisibility rule. We can't generalize it. And the witness or the counterexample that was presented was 1899. You'll easily see it's got the same digit sum. I've just made the 9 into a 1/8, so still adds up to 27. But even without factoring this, I claim that to get from 900 to 1899, I have to add what? 900. So if I have a multiple of 27 and then I add something that isn't a multiple of 27, but it's a multiple of 9, then this cannot be a multiple of 27, okay? Yeah, so that's, I think, what I want to say on that one. Okay. All right. What's up next? And there are lots of counterexamples. I saw, and I'm not going to shame students. Obviously, I'm not going to name names, but someone said 1992. Well, the problem with 1992 is that doesn't satisfy the hypothesis that its digit sum is a multiple of 27. And then I think I also saw people that presented multiples of 27 that, well, they might have been doing part A. So you have to make sure that the conditions or the hypotheses are satisfied. All right, so here is a geometry problem. This one may take a little bit of time to process what it's saying, and be careful on this one. It seems like some people are having video problems. I've definitely seen, well, one person has submitted the correct answer, so you need to pin your video. My video is pinned. Oh, you're saying this to the participant. Yeah, if you want to see just this problem up close, yeah, right click and do pin video in Zoom. So someone already did find not only the answer I had in mind, but well, the minimal answer, as far as either they gave a very short proof or a short counterexample. So I've underlined the things to pay particular attention to. I'm getting a lot of people, and this happens almost every time I give this problem, that say, well, no, because knowing our congruence postulates, side would tell you that, no, we can't have a situation like this. I would agree if I told you that, let's say, triangle T1, just to pick one of these, if we knew that it had all different sides, I would agree that side will guarantee that they have to be congruent, so this would be falsified. And moreover, if T1 were equilateral, so all the sides are the same, then, by same reasoning, if this condition, this sort of elongated, sort of dual kind of condition is met, then yes, this would also be false for equilateral triangles. But we've skipped over a case, and that's something that needs to be think about. So it says there is a side. We can repeat sides here based on the wording of this. That's not excluded as an option. So given that, let's think a little bit more about if we can come up with an example that will convince ourselves whether this could be true or not. And if you have an example, send me like 2 triangles, just, whatever length, like 3, 4, 5. I mean, that's not going to be it, but. Okay, so just to interrupt here a little bit, I don't want to spend too much longer on this one because we have a lot of these to get through. I'm getting a lot of people that say, this is true. And then the examples of the triangles that they're sending me, well, at least one of them, it has the unfortunate property that it doesn't satisfy the triangle inequality. So like, for example, this isn't a triangle, or it's at least a degenerate triangle. So we're not going to count this as a triangle. So you have to make sure that when you send, when you think you have something, that you're sending an actual thing that could be a triangle. Okay? So I'll just move on and start talking about this. So I kind of, in sort of running through how to parse and interpret the problem, said that, well, if we knew ahead of time that we have a scaling triangle, then yeah, it's got to be, you know, they have to be congruent if we have these sort of, you know, pairwise conditions. And if we knew ahead of time it was equilateral, then same reasoning, side, 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 it's got to be true. I am also seeing cases like people have submitted things like this. Again, these are not triangles because 3 plus 1 is less than 5 and 2 plus 1 is equal to 3. But the thing is, what I'm mystified by is that I think one of these conditions would hold, so I think the other examples I got were like 3, 3, 5 in this, or 2, 2, 2, 3 and this. So I think in one direction this will work, but it won't work in the other direction. That is, 1 is not a side of this, 1 is not a side of this. So even if these were triangles, the case that I skipped over is you have that they are isosceles, but not equilateral. And perhaps the simplest example, that looks too equilateral. Let me do, let's say this was a 2, 2, 3, and then of course this isn't to scale, but, and then a 3, 3, 2. So let me, just for organization, say that this could be T1, this could be T2, and I think it's easy to see that all of our required conditions are satisfied. Now, I've seen probably, I don't know, 25 messages at least come in, right? And unfortunately, I've not been able to, because I can't type fast enough and think fast enough, respond to everyone, which I regret. However, hopefully in my discussion of like how we come up with this example, and hopefully we're convinced that, yep, for each side, we can find a matching side that has the same length, and that goes for T1, I can get a 2 and a 3 out of T2, and then in T2, I can get my 2 and 3 out of T1. It's just that the 2 is repeated here, the 3 is repeated here. So anyway, that's just a little kind of cute tongue twister that seems like it's a obvious, well, it's just side, side, side congruence. Okay. How about this one? Back to algebra. So I think people have, well, one student has initially messaged me what he thinks the answer is as far as, is it true or is it false? So that's the important first step, is try to get a gut feeling, maybe based on empirical evidence. So not necessarily hard proof, but just based on your experience or based on your sense of, you know, is this how the rules of algebra work? I mean, this is sometimes called the freshman's dream. I mean, wouldn't it be a great thing, an easy thing for a freshman in algebra class to just say, okay, I've got this equation to solve. Let's just say these are all functions of x. How about I just take the reciprocal of each term on each side? That should be fair, right? I mean, equal treatment for every term, right? So it looks like, and this actually came from a 7th grader one time. She was in my class. She probably hadn't had a full year of algebra, and she thought, well, I should be able to do this and get this and then solve this. And then she was wondering, why isn't this working? So we had to kind of explore this a little bit. So it may be true under certain conditions. In fact, if you have heard of programs such as the Ross program, or its Boston area brainchild or sort of sister program, PROMISE, Program for Young Mathematical Scholars, they have an acronym, and this stands for Prove or Disprove and Salvage, which is just a fancy way of saying, see if we can modify some conditions to make it true, if possible. So I have already seen, although I have not been able to respond in the chat window, that some people have said, well, it's true if this condition, this additional condition holds. So that would be salvaging. If we can make a simple additional condition that's easy to state, then we might be able to make this into a true fact. Okay. So I got this from one student. But I don't actually agree with that, because with fractions, it would be, again, a nice dream come true if we could just add denominators. But that's not how fraction addition works. So this does not work as an example. However, so what is on my camera is everything that is written. So if you can't see everything, then you should probably right click and pin video so that you can see everything. I suppose I could zoom out a little bit. Get a greater field of vision, but this is everything. Okay, I very much like the answer that I just got, and this is indeed the way I convinced this student that that this is in general not true. If we look for small numbers, like don't pick A equals 37 and then try to find B, C, and D that satisfy this. Think small. 1 doesn't seem like a good value of A, but and 2 and 3. But if we just look at, like, what if, like, there's nothing that says that these all have to be different integers. If I just pick 1/4 plus 1/4, that's clearly 1/2. And when we learn fractions with, simple, like, single-digit denominators, we also learn about reducing fractions or creating equivalent fractions. So we also learn that we could have 1/6 and then 2/6, which is really just equal to 1/3. And that equals 3/6, which reduces to 1/2. So to summarize, the fraction does not have to be in simplified form. There was nothing in the statement that required that, like, when you add them, that it's a reduced fraction. So good question. So here's an A. There was a question that came in, can these be negative numbers? Well, it says integers, so there's nothing that prevents you from doing negative numbers. And I want to come back to that because that's a very good point. So if we made our A and B both be 4, our C be 6, and then our D is 3, because 2/6 is not reduced. We were dealing with what's called a unit fraction, a fraction whose denominator or numerator is 1. Well, these both satisfy the hypothesis. 1/2 is equal to 1/4 plus 1/4, and 1/2 is also equal to 1/6 plus 1/3. Yet 4 plus 4, not the same as 3 plus 6. So that's a disproof. I thought about a little bit, well, would the problem be trivial if you have negative numbers? Like, here's an example. 1/13 plus 1 negative 13th equals 0, and that equals 1/7 plus 1 over negative 7. What's wrong with this example? Someone messaged me, private messaged me. What's wrong with this? I thought, oh, that makes it really easy if you let negative numbers. So I have to say they're positive integers. Actually, no, this doesn't work. Why doesn't it work? Well, the sum of these fractions is 0, so this hypothesis is met. So yeah, I think I've gotten enough responses. The problem is these denominators themselves, 13 and negative 13, have the same sum as 7 and negative 7. So yes, the second condition does not work. So this does not work as a counterexample because this equation is actually made true. Now that doesn't mean that you can't find an example with negative numbers. It's just that we can't have like negative numbers with equal absolute value in different signs, right? So we can't just do this trivial sort of like make them add up to 0, okay? All right, so let's move on to something else. Here's a quick one. This should be quick. So, by the way, if you are unmuted, please mute yourself, or I think the Dr. Pillay or Ms. Mack will mute you. Please also turn off your video, just so we don't get that on the recording. So, can everyone see this? I'll just read it. Prove or disprove. Okay, great. I'll share some of the answers I got initially. Do we agree? What's wrong with these as counterexamples? These aren't even, so they got to be even. For some reason, the example that first occurred to me is you just write 6 2s in a row because it's the same digit and they clearly add up to 12 and the last 2 digits is not a multiple of 4, so this can't work. But if we're thinking smallest counterexample, that'll just be 66, right? So, okay. So this is a disproof. Okay. What else do we got? Let's go back to, oh, great question. I thought I was about ready to move on, but I got a great question. What about 84? So let's look at 84. Indeed, 84 has a digit sum that is a multiple of 12. And 84 itself is a multiple of 12. But be careful of understanding the logic of what this claim is saying. It's saying, and I'm circling or underlining the keywords. So if I have an even number, that means among all even numbers that satisfy this hypothesis, n, the even number, is divisible by 12, then it must follow that the original number is also a multiple of 12. So someone has said, well, it's not always false because 84 works. And so this is a sort of a case of it's sometimes true. 0 is a multiple of 12. So 0 would also not work as a counterexample. So there are many examples of even numbers that have digit sum that's a multiple of 12, and they themselves are a multiple of 12. But I'm just saying among all even numbers I could think of, and indeed the smallest one is 66. You can see that that's not a multiple of 12, despite the fact that its sum of digits is a multiple of 12, okay? So, yeah. Okay. This one is a longer one. And I want, well, we've done algebra, we've done number theory, we've done, you know what? This is kind of a classic, but I want to make sure that before the hour is up at least, because maybe some of you might have to go at the top of the hour. Hopefully some of you can stay for another half hour or even up until 4 p.m. But this one is a counting problem. And it's a little bit long. By the way, I am named Chris-NYMC. If you are seeing or pinning NYMC online, that is Dr. Pillay. So you want to, I should be second or third in the list. You should, you know, click on my name and right click and pin that if you want to see the problem. Unfortunately, I can't read it out because there's geometry here involved, and so I can't really read figures. So for this one, because the messages are coming in at a little slower rate, So I had a request to, let's see if I can do both of these in the same window. Trying to also okay, I got a request to, let's see if I can do this simultaneously, project this as well as the digit sum problem. Can't really do this unless I zoom out. Even then, probably not going to be very successful. Let me see if I can. Okay, tons of chat messages have come in. So I'm gonna quickly drown in chat messages. Yeah, someone suggested maybe doing this, see if I can. Okay, I think we got everything. And by the way, there will be a handout that will be made available afterwards. I will send it to the organizers, they will circulate it. This one definitely slows people down. And this was actually one of the first problems presented in my geometry class, my honors geometry class. You can see how it has a geometric flavor to it. Circles and chords, and you're basically drawing all possible chords and diagonals given that you've got, you know, in general, endpoints on the circumference in general position. So people that have done the n equals 5 case will see that the answer is, for n equals 5, 16. And I'm not going to draw it out. So that's the answer for part A. So 2, 4, 8, 16. It is very tempting, therefore, to say, well, if in general I have n points in general position, these are all powers of 2, so shifted by 1. So 2 to the n minus 1 is a tempting conjecture to make. But the point of this geometry problem, and actually at the heart of it, it's not even so much geometry as much as careful counting. And I'm not going to get into the argument. That'll be sort of an exercise for you to think about. And it'll also gauge, for example, if people want to get a hint on how to prove this or what the formula should be, you can email me. I have on the Uber handout, it's like 4 pages, and it's got all, it's got the opener problem, and it's got 19 other problems, including 3 open questions that are not even known, but just to, you know, expose the fact that there are some classic open questions that are actually very simple to state, but which we don't know the answer for. Okay, so I've got a handout of 20 problems, and at the very top is my email, which I'll just write it and I'll message it to everyone here just so you have it. So it turns out that in the n equals 6 case, other than getting 32, which would be what you would expect, it ends up being 31. So the pattern that looks like it should be a pattern, you know, like 4 data points does not constitute a proof, okay? So we know that it's not this, or at least it's not that simple. And it's not even exponential. I believe it involves some binomial coefficients and being careful about your counting and how you draw in the diagonals of a general sort of n-gon. My email, and I'm going to message this to the entire group, but I created it just for this bunch. Chris, NYMC at outlook.com. So if you if you send me mail asking about particular problems that you had questions on or would like hints, or if you missed getting the handout, although I hope that, you know, the organizers will make it available and have it on a website or have it somewhere that everyone can access, you can email me there and I will just message it to everyone. My email, Chris, NYMC at Outlook. So one student looked this up and it turns out that the actual formula is 1 plus n choose 2 plus n choose 4. That may be suggestive as far as now you sort of know what to go for. But in general, if you're a mathematician and you're working on something like this, you're not going to have you know, OEIS, online encyclopedia of integer sequences, or you're not going to know what this is. You're going to have to come up with a conjecture that is consistent with all the data. Okay, so I got 2 questions, so I feel obligated to answer this. What is choose? So another way of writing this is 1 plus CN2 plus CN4. So what is that? Basically, n choose 2 is the way of the number of ways of choosing 2 distinct objects from a group of n distinct objects without regard to order. Okay, so if I had n distinct objects, there are n factorial ways to order them, and well, let's put it this way. If I have n distinct objects, I have n choices for the first, I have n minus 1 choices for the second, and then if I don't care about the order of these, then I just divide by 2 because I could have chosen them in either of 2 orders. And in general, this is n factorial over 2 factorial times n minus 2 factorial. Let me adjust my camera, apologize. Okay. And similarly, n choose 4 is, all right, now I want to choose 4 distinct things out of a group of n. Then, you know, n choices for the first, n minus 1, n minus 2, n minus 3, and then I end up dividing by, instead of 2 factorial, 4 factorial, and then n minus 4 factorial. So this is just a notation, and apologies if you haven't seen this. I could write out an exact expression. In the interest of time, though, I'm going to move on. And I know that a number of people have joined late. And so I'm wondering if we can just do a repeat of something that we, unfortunately, I don't have multiple copies of the, actually, maybe I do. So the theme of this talk is finding examples and counterexamples when I present statements that could be true, could be false. So let's just consider this one again. And for the rest of you who have already sort of soaked that up and have gotten what you're going to get out of it, we're going to move on to a longer one. So if you joined late and didn't get to see this one, play with it and message me what you think, if it's true or not, and then also message me what you think if it's true, give me a proof. If it's false, give me a counterexample. So this is a new problem. It concerns so-called semi-perimeter points. It's a longer one. So this will take a while just to read and understand. So I'll shut up and let you read it. So for the benefit of everyone who was wondering, what do I mean when I say n choose k, I just sent a message that should have gone out to everyone. I first defined what it is from a combinatorial perspective, and now I will give the formula. By the way, I got Ms. Mack said that the words are too tiny. If you pin my video and my name is Chris-NYMC, it should be at the top. You should be able to see that and like maximize your window so that you can see it. I assume people are able to see this, but let me know if there are a lot of problems. Okay, so I want to start talking about it because I think I've gotten a lot of responses that suggest that people know what's going on here. So just to sort of talk through this in my own words, you imagine that you are a person or an ant and you are traveling along, you're like walking along the perimeter of the triangle, and you traverse or walk a distance equal to half of the perimeter. And then you end up at a point. And that point that you end up relative to where you started from is called the semi-perimeter point, okay? So in this example of an isosceles triangle, if I start at P, it's pretty clear that I have to end up at the midpoint on the opposite side. Now, you may wonder, well, does it matter which direction I go? Like if I go this way, which is counterclockwise, could I conceivably end up at a different point than if I walked in the clockwise direction? So is it possible that I end up at like 2 different points? Is that possible? That's just a... So I see no. Yeah, you will end up at the same place. So the idea is, if it did turn out that I ended up at different points, well, then this piece of it would be the semi-perimeter, and then this piece of this would also be the semi-perimeter. And so 2 semi-perimeters give you the whole perimeter, which means that there can't be anything between these points, okay? So, right. Okay, so we've got that out of the way. I wish I printed out a different one of these, but actually I'll just draw on this page here. If I go quiet, it's because I'm usually messaging someone. Okay, so we've agreed that we can go in either direction, right? So now let's just take sort of an arbitrary triangle here. And, well, let's just label it A, B, C. So let's suppose that this was false. Well, then that means that I'm going to be on either AB or AC. And without loss of generality, I'll just assume it's one of these because, you know, I could have gone in the other direction and, well, anyhow. So let's just suppose that my semi-perimeter point corresponding to point A lies here, okay? And so, actually, because I want to make the variables kind of work out nice, I'll just assume that I landed on AB somewhere. Okay, so if I use lowercase letters to represent the lengths of sides opposite their corresponding vertices, then this length will be A, this length will be C, and this length will be little b. And moreover, if we landed on a point that was strictly between A and B, for example, and the exact same argument would work for A and C, that's why it's a without loss of generality, it's kind of arbitrary, then that would split the length of C into, let's say, C1 and C2, okay? But if I start at A and I get to point S, and that means I've traveled a distance of C1, then the implication is that's half the perimeter, and that's equal also to if I had gone the other direction, which is B plus A plus C2. Okay? But what do we know? Well, we know by the triangle inequality, B, or A plus B, is greater than C. The sum of any two sides is greater than the third. Okay? So in particular, B plus A plus C2 is certainly greater than C, but the problem is that that means that C1 would be greater than C, which is an obvious contradiction. C1 is strictly less than C. So this is sort of a proof by contradiction to get two inequalities that contradict one another. Okay? So, good. I think we got through that one. Did well on that one. I did see, by the way, for people that joined late, there was some good work that came in. I wasn't able to scroll up and get back to all of you who did message me answers. So apologies for that. This is flying by really quickly. I'll just talk about this one briefly. This isn't an actual problem to work on. This is the Goldbach Conjecture, which says that every, oh, I've got a question. What does that mean the answer is? So prove or disprove. This is true. I always land on the opposite side when I start at a vertex and go to the corresponding semi-perimeter, okay? So, maybe some of you have seen the Goldbach conjecture. So I'm just going to talk about it. It's very celebrated and famous and old. It's almost 280 years old. And it says that every even number, I can write it as a sum of two primes. It doesn't need to be a unique expression. For example, 18 can be like 5 plus 13 or 7 plus 11. Are there two different expressions for 20? We can't say 19 plus 1 because 1 is not a prime. Well, 20 is 17 plus 3, and it's also 13 plus 7. Okay, so there could be multiple representations, but the point is this was conjectured a very long time ago before there was technology and computers, and it has been verified for just ginormous, large numbers. That doesn't mean it's true, though. I can think of statements that are fairly simple where the smallest counterexample is like 15 digits long. And for every number less than that 15-digit number, it's true, okay? So either it's true, in which case we like to think that a proof may be available. It may be that we are living in the wrong century. If you know about Fermat's last theorem, that was 300 plus years old before it was solved by Wiles, Andrew Wiles of Princeton in 1995. And it is largely thought that Fermat who thought he had a very elegant proof that was too small to contain in the margin, that he probably didn't have a valid proof, that there was probably a flaw in his proof, because the mathematics that is required for the known proof of Fermat's last theorem is mathematics that just was not available centuries ago. It had to be developed and invented. So it could be that we don't have the right machinery and tools. People are still trying to figure it out. Progress is being made on various things involving primes. This gets into analytic number theory, which gets very complicated very quickly. It's a fusion of calculus and analysis and number theory, which is kind of beyond the scope of this. But think about it. It's either true, in which case we'd like to think that there is a proof that's within our reach and that it should be an elegant proof. There's some controversy around computer-aided proofs, like a computer search up to like 10 to the 100th has shown that, there's no counterexamples. And then beyond that, maybe we can make certain assumptions if we know that we're in like numbers that are that large territory. We can create bounds and we can do things. But in general, conjectures that involve primes are very hard to make progress with, especially open conjectures. But there's the flip side. Maybe it's false. Maybe there is, and if it's false, then there's going to be a smallest counterexample. Now, of course, the curiosity would be, what would that look like? And well, obviously, to verify that it's a counterexample, we'd need to show that every way of expressing that number as a sum of two odd numbers, that at least one of them would have to be composite for every such expression. And that would probably be a computer-aided proof. But then it leads to other questions like, are there more? Are there finitely many counterexamples? If so, can we make a classification about what numbers will act as counterexamples and what numbers will not? And you could make that statement, well, if it's finite, then generally something interesting must happen after you get the largest counterexample, such that, you know, like I said, with the 10 to the 100th, you're able to make an assumption that you can use in a mathematical proof. But if there's infinitely many, we want to dig deeper and say, all right, what is special about those numbers that makes them counterexamples? Someone else mentioned the twin prime conjecture. Twin primes are primes that are 2 apart. So 5 and 7, 11 and 13, 29 and 31. We don't know if there are infinitely many twin primes. Ironically, we do know one thing about it, which is if I take the reciprocals of all the twin primes and add them together, regardless of whether it's a finite or infinite sum, that has been proven to converge. And the sum of the reciprocals of the twin primes converges to a number called Brunn's constant, which is trying to just look it up real quick. Approximation of it. Approximately 1.902. Now, for people that have asked, I've gotten questions about like how old is this conjecture? I don't know all of this stuff. I'm not like encyclopedic there. So for that, unfortunately, in the interest of time, because I do want to move on, we are about 22 minutes past the hour. I'd like to move on to a different problem. So look it up, maybe take a note, so let's move on. I want to move on to a pair of problems. And again, sticking on the number theory theme, these two kind of go together. So we'll ask the first one, and I think we'll answer it pretty quickly. Do it. I think you should all be able to give me an answer fairly quickly. Okay, I'm getting, oh, you know what? I gave this in the wrong order. I gave the harder problem first. Let me see if I can fix this. Da, 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 da. See if I lost my papers. Well, whatever. The first part of this was going to be, I have so much paper around that I'm sure it's somewhere here, but the first part was going to be, so forget about this, is if k is not a multiple of 5, then 12k plus 5 is prime. So this is like part A. This is part B. That's why I printed both these out. But so for part A, just forget about the finitely many. This is the harder version of it. So if k is not a multiple of 5, then 12k plus 5 is prime. Is it true or false? I'm getting a lot of trues. So let's make a table here. And if you say it's false, give me a counterexample. That is, give me something that's not a multiple of 5, but 12k plus 5 is composite. I'm saying for every, okay, so someone said true because k equals 2. So certainly let's just start listing these out in a table. If k is 1, then I get 17. That's prime. If k is 2, then I get 24, 29. That's prime. So, but I'm saying for all values of k that are not 5, is it always going to be the case that 12k plus 5 is always going to be prime? So we have infinitely many values of k to think about. So what do we get when we plug in k equals 3? We get 36 plus 5, that's 41, that's prime. So far these check out. When k equals 4, I get 48 plus 5, so that's 53, and that's prime. Actually, k can't be a multiple of 5, so we're going to skip over that one. So on the basis of the first 4 values that I tried, if you didn't know about some of the advanced results that I've heard people citing about Dirichlet's theorem, you might say, well, this could well be true. But now what happens when we put in k equals 6? We get 72 plus 5, and that is 77. So that shows that here's a value of k that is legal, except that 12k plus 5 here isn't prime, okay? So that's the first part. Now let's shift our attention. So, okay, so we know that it's not universally true, but the next question then becomes, okay, just like I was asking for the Goldbach conjecture, we want to know if it ends up being false, are there finitely many counterexamples or are there infinitely many? So we have one counterexample here. Is it true that we have a finite number of these that make this composite, or is this going to be an infinite set is the question. And I think I saw people right off the bat indicating that they think they're infinite. I'm wondering if someone can offer up a proof, and ideally one that doesn't rely on advanced results. Like, in other words, everything that you quote, you need to be able to prove. So some people say finite, some people think it's infinite, but what we're seeking here is a proof. We're seesawing between, I'm getting a lot of messages. About half of you think it's finite, half of you think it's infinite. So let's talk through what a solution would look like in either case. If it's finite, then that means there should be a largest value of k that makes this composite. So in other words, if I listed out more values of k, there will be a largest one. And somehow we have to prove that when we get bigger than that, then we're always going to end up with a prime. And in general, proving results about numbers that end up being prime, like this would be a very simple prime number generator if that worked. But you may have heard that it's actually very hard to generate like new primes. Like typically the largest primes that are generated are called Mersenne primes. They are 1 less than a power of 2, okay? So that would be how you'd have to proceed if you thought the answer was finite. So maybe people have a gut feeling like, yeah, you know, there's only going to be so many of them, and then after that, everything's going to be prime. Someone messaged GIMPS. That's short for GIMPS, Great Internet Mersenne Prime Search for supercomputers. Okay. Now, on the other hand, what if it's infinite? If there's an infinite family of values of k, and I'm not saying that you have to find all the values of k that make this composite, but you should be able to demonstrate a construction or show me how to generate values of k that make this composite. And sure enough, it is motivated on this idea of 77. So screen is fuzzy. Are other people seeing the screen is fuzzy? I didn't change anything in the camera. Okay, good. Trying to doing like origami here with my paper. I'm trying to fold stuff up to make more white paper. Okay. Okay. So if we write this out, we have a true equation. So I claim that this is also going to be composite. Basically, if I add a multiple of 77 to this, then if we expand this out, we get 12 times 6 plus 5 is 77, plus 12 times 77n. And we can always factor out a 77, and that's composite on its own, but then we also get the other factor. So it's even more composite because I have another. So this would be an example of a construction. There is one so I've gotten a barrage of repeat messages, so I'm not sure if that's a Zoom bug or if it's just people just going repetitive. But anyway, let's try to keep chat. Sometimes I guess Zoom, I don't know, does weird things. Sometimes they queue up messages, and then like at the end of this, I might see messages that came in at like 11:40 or something. So anyhow, now I claim that there is one thing about this that we have to be careful about. Can anyone tell me what that is? One sec, I just got to deal with something here. I'm getting spammed by chat. Allison Coven, I'm messaging something about just something I'm seeing, so please take care of this. Okay, so I'm trying to scroll. Unfortunately, I got like almost like a denial of service of I've got like hundreds and hundreds of like messages from this. I don't know if it's a bug or if it's a bot or what the heck is going on, but I'm scrolling through a sea of messages. I think though somewhere along the line, I did see what the answer ended up being, which is what if n were equal to 2? I get even n has to be excluded. I don't agree that even n has to be excluded. And n equals 4 would work. Why should even n be excluded? But what happens when n is equal to 2? I get 77 times 2 is 154. That ends in a 4. And then this would presumably be my value of k that is a counterexample, but then I'd get 154 plus 6, and that's 160. But we said that the rules for k are that k cannot be a multiple of 5. So we do have to modify this a little bit, and we have to develop a criterion on n to make sure that this thing does not end up being a multiple of 5. This is a little exercise in number theory, modular arithmetic. So I apologize that so many of these are number theory ones, but as I suggested for the when I flashed this on the screen earlier, where is it? Oh, this was my original problem. So just so that's how it got lost in this sea of paper. So my apologies. Give me a sec to get reorganized here. Oh yes, I mentioned participe. It turns out that when you learn number theory, there are lots and lots and lots of conjectures. There's conjectures with congruences. There's conjectures with multiples. And so there's lots of problems that are of this variety. This is one that I learned about a year ago, and I think it is a wonderful problem. And I'll let you use a calculator if that helps speed things along, but here it goes. This is a prove or disprove. Don't worry about the salvaging part. Oops, sorry, the screen seems to be a little fuzzy. Okay, there we go. If n is prime, sum of digits of n is either prime or it's even, or both. There's only one case where it'll be both prime and even. So to be clear on what we want and what success looks like is, it's not a matter of just write down a prime number and show me that the sum of the digits is even. I'm saying for any prime number, is it always the case that the digit sum is going to be prime or even? And so if it's yes, then prove it. If it's no, then that means that there will be a number that is prime, but its digit sum is odd and is composite, okay? So that's how this one's going to go. And this one may take a little bit longer. So I have two people so far that think it's false, and I have one person who thinks it's true, and then the rest of you haven't yet registered an opinion. But then again, if it's true, then that means that we should be able to come up with a proof such that for all prime numbers, we can somehow reason about the digit sum, which seems awfully hard to do. Okay, so I'm getting a number of answers that are not expected. So someone thinks that 63 is a counterexample. 63, though, is not prime, so that fails the hypothesis. I get 37, and that makes this a true statement, but I'm saying 37 is just one of infinitely many primes. Okay, so 37 indeed has an even digit sum, but we have to be able to know that this works for all primes. Here's another one, 61. I agree it's prime. I agree its digit sum is prime, but there's many more primes, and 13, there's another one. So these are all examples that show that this is true, that satisfy this statement. I'm asking, is there an example, and let's be very clear on the logic of this, because this is a little bit tricky. If this is false, then that means that I can find a prime number and its digit sum is not prime and not even. What does not prime and not even mean? It means odd and composite. So here's another way to rephrase the premise. Can I find a prime number whose sum of digits is an odd composite number? And thus far, no one has gotten anywhere really in the neighborhood of what I'm thinking of. So here's two more. It seems like this one is really kind of throwing people here. 2 being the smallest prime, the digit sum of a single digit is just the digit. So 2 is a prime number and 2 is indeed even. So this just means that 2 satisfies the statement. 11 is also a prime number and its digit sum is 2, but again, that just means that 11 works. We have infinitely many primes that we need to go through. So what I'm looking for is not just examples of, okay, here's a prime and the sum of its digits is one of these two things. We need to if we think it's true, we need to be able to do an argument that will work for any prime number work. So I finally got a right answer from someone. So let me just, because I think people are still perhaps not understanding this. And again, we went through this at the beginning, but it's probably worth repeating. I got another correct answer. So some people say, well, 13 would disprove this. And I disagree. 13 is prime, and the sum of the digits of 13 is 4, which is even. So 13 doesn't work. Someone said 61 doesn't work. Well, 61 is prime, but the sum of the digits of 61 is 7, and that's prime. So that also doesn't work as a disproof. So maybe I should just write it down. Disproving, sorry, I'm gonna minimize the chat window so that I can see what I'm writing, make sure I'm writing it on the screen. Did I lose my marker? Oh, no, okay. So disproving this, so I'll just tell you, this is actually a false statement. So now I've kind of maybe spoiled a little bit of this, in that you know that this in general is not a true thing. So, but disproving this means finding a prime n such that S of n, and that's just my shorthand for the sum of the digits of n. I'm gonna move this up. Is odd and composite. So maybe a way to think about this that will help is what could be the sum of the digits that would be odd and composite? Well, let's list our odd numbers. 3, 5, 7. Okay, those all fail because they're all prime. Could S of n be 9? Well, if the sum of the digits was 9, what problem does that present? Yeah. If we if the sum of the digits was 9, as a matter of fact, if the sum of the digits was a multiple of 3, then that means that this part of the hypothesis will be falsified. Okay? So we skip over 9, we skip over 11 because that's prime. So maybe the right thing is figure out what the smallest possible digit sum would be that is odd and composite and not a multiple of 3. And maybe working backwards from the digit sum, we can construct a counterexample. I will tell you that the smallest counterexample is a 3-digit number that is very close to 1,000. Okay? I'm going to suspend doing more, I guess, discussion here because we have a hard stop at 4, and I want to leave some time for questions. Actually, I'm gonna reply to a few chats. So now I think people are starting to get it. Okay, now I'm seeing a flurry of messages coming in now, so I can definitely tell people are now tracking. It's easy to misread it, I guess is what I will say. So I'm trying as fast as I can to message everyone who is getting, and everyone's getting the same smallest counterexample, so that's a very good sign. So, and I did say in the interest of time that you could use a calculator to tell primality. So I'll give this another couple minutes and then we'll switch over to doing questions for maybe 5 minutes. So there is, in fact, a counterexample. If you see me going quiet, it's because I am feverishly replying to chats as quick as I can. I want to give everyone an opportunity to hear from me. Okay, we're at 10:02. So I'm going to stop replying to chats for the moment. And I guess when this meeting ends, then the chat session will go away. And I will, for the benefit of those who joined late, I will once again send everyone on chat my email address that you can email me. Okay, so that's my email address. One more reply. Okay, so what you realize when you go through the odd numbers is, just one sec, I'm replying to Dr. Pillay. Okay, so when we go through the odd numbers, we want something that's odd and composite. And we said that if the sum of the digits is a multiple of 3, then we're in trouble, because then that means that n can't be prime because it'll be a multiple of 3. So that rules out, and by the way, I will switch off my camera back to me. Actually, you know what? I'm gonna change my shirt just for a sec. No, not because I'm sweating, but to pay homage to the New Yorkers. I consider myself a displaced New Yorker because I went to school here. So this is the New York State Math League shirt. I have the other one, which was like patterned after the I Love New York. So, so let's see. I'm trying to do two things at once. Let me switch back to this so that we can finish talking about it. What I was starting to say was that we need an odd composite number and something that's not a multiple of 3, because then we know that we're not dealing with a prime number. So 3, 5, 7, those are prime. 9, multiple of 3. 11, 13, prime. 15, multiple of 3. 17 is prime. 19 is prime. 21 is a multiple of 3. 23 is prime. 25, though, presents itself as this could actually be the sum of the digits. And what are the smallest numbers that have a digit sum of 25? Well, there's 889, so 2 8s and a 9, and then that could go in any order. It could also go 988 or 898. The trouble with these is these fail to be prime clearly because they're even. And this, it turns out, is also not a prime. It's a multiple of 7. There's one other, though. There's 997. Its digit sum is 18 plus 7 is 25. So we have that the sum of the digits is odd and composite, so it's not prime and it's not even. And sure enough, if you do testing, 997, it turns out, is indeed a prime number. So it is not always true. And people came up with different examples, but 997 was the one that I saw like over and over and over again once people sort of understood what the question was asking. Okay, so yeah, this one was I really enjoyed this one when I got it. Let me just go through a few questions that I saw queued up. Someone said it would be great if you could give some references for these problems. I wish I could, and I will try to when I can. I will say though that like maybe half of them I just made up. Okay, so the references are original. Okay. What else? Do you write Amy problems? Yes, I do write Amy problems. I have written over 50 Amy problems since 2002, and I'm still writing them and still on the Amy editorial board. I'm wondering in the last couple of minutes, because we have less than 5 minutes, and I would like to wrap up like in kind of probably 1 or 2 minutes, ideally, to give Dr. Pillai some time to transition off of this. So are there any other quickies that I might be able to answer for the entire group that you can message me? And once again, you have my email. My email will be on the handout at the top so that you can send me offline if you have questions. What do you do in computer science? Well, obviously I learned programming in college, but what I do now at Microsoft is I am a security program manager. So everything from you hear about Russian hacking of the elections that happened in 2016. So I've written in a number of languages: C++, C#, Python, JavaScript. Oh, someone is saying the camera is giving them vertigo. I apologize for that. So, in fact, let me tidy this up. Okay, so other quickies that came in as far as chat messages. Let's see if, I went to Cornell University, so upstate New York, so that's why I consider myself a New York at heart. Any tips for rising competition participants? That's not a short answer. Lots of practice, I guess, is one thing. So do I know Po Shen Lo? Yes, I do know Po Shen Lo. I've worked with him at the Math Olympiad Summer Program, which I've taught at. So I'm going to stop answering questions, and I'm sorry if I didn't get to your question, but please email me. You will get my email on the handout that will be forthcoming, and you'll get a bunch more problems that we didn't even get time to get to. So I really enjoyed doing this. I hope you got something out of it. Yes, I know Richard Rusick. I know a lot of people in the math community. I appreciate your attention to all of this, and I just want to say one thing about just the times that we're living in. This is kind of the mushy, poignant part of the talk, where, 5 months ago, I don't think any of us thought that we'd be here doing this in a virtual forum and not knowing when we were going to go back to life as we knew it. And so it's very unsettling. It's very, you probably know people who have been affected by this, and it's hard. It's hard not getting to see each other. And I hope that this gave you a little break from just the stress of, being inside or not being able to hang out with your friends. But really be there for your parents, be there for your teachers. We're here to support each other. And, I consider all of you my students, even though we haven't known each other for long. So I hope that we're going to have a, that I'll hear from some of you on email, because I look forward to answering your questions and kind of maintaining contact. And let's hope that one day we do get to meet each other at a future New York Math Circle talk. Okay, so the last parting shot I'll say is, in these uncertain times, I know it's very dark and scary, but I'll say, and let me just switch back to, so you see me one more time, Be brave, be strong, and don't be afraid. Thank you very much, New York. It's been great.
Thank you, Chris.
Good luck.
Okay,
Thank you, Coven.
Okay, Chris, just one moment of your time.
Yeah, sure.
Where it says chat, do you see at the bottom, there's a file icon?
Yeah, let me just get that really quickly. Right
at the bottom, where you actually reply to messages.
I do not see that, but what I can do is I can select all and copy, and that's just what I'm doing. So
Okay.
that maybe you see that as the host, but I don't see that. I see it when I want to send something to everyone, but yeah, no, it's good. So if you want, you can end it now. I think we're done.
Great.
Okay. Yeah.
Thank you.
Yeah.
Bye.
Sure. Bye, guys.